Hey, so we're just tootling along with this textbook and just making all kinds of progress, except I'm skipping the chapters. I don't feel like I want to do, or sections at least. Okay, this is energy. So we did kinetic energy. Now we're going to do potential energy and conservation of energy. So if you remember, if you watched any of the other videos, I talked about this lady, and her name was Du Châtelet. And she basically was like, okay, guys, what Newton meant to say was blah, blah, blah. And she translated it into French for like people who shockingly didn't speak Latin. And it's really interesting because whenever you kind of read through some of her stuff, which I'm acting like I've really done, but I've like skimmed it and asked ChatGPT to summarize it for me. Okay, maybe not quite that bad, but pretty close. Is like they really didn't understand the difference between forces and energy, and so we're like just presenting this like clearly potential energy is a thing. Like you should just know this and that it's super obvious. But like I think Du Châtelet describes potential energy as like a dead force and kinetic energy is a live force, but they're not really forces because it's something like they knew that they were onto something, but they didn't know how to describe it. So anyway, it's just really cool if you ever get into the history of science, like that it wasn't always super obvious that, you know, kinetic and potential energy was a thing. So if you took some kind of high school physics, you probably learned something about potential energy, or you've heard something like, you know, if you're at the top of a hill, you have mgh. And if you're at the bottom of a hill, you have 1/2 mv squared. So basically, this would up here would have been your potential energy because you have the potential to fall. And the kinetic energy is how fast you're actually going. Okay, so potential energy is always based on position. Okay, so come here. Okay, so potential energy, I don't really like this orange, and I keep using it because I'm too lazy to pick a different color. There we go. Okay, so potential energy, it's always based on position. Okay, this is important. And then kinetic energy, I can't spell, kinetic, come on girl, kinetic energy is always based on motion and based on motion. So things can have potential energy, things can have kinetic energy. And I remember, and I don't know, I'm sure your book's going to get into this in a minute, but for the purposes of me being impatient, I'm just going to go ahead and do this now. I always remember in high school, and even in college, I remember hearing initial kinetic energy plus initial potential energy equals the final kinetic energy plus the final potential energy. But this is actually not true, okay? There's an asterisk here, okay? So the idea is that energy can neither be created nor destroyed. However, in the systems that we're looking at, energy can be, like, so yes, this is true if you look at the universe. But if I'm looking at a system like a box being pushed across the floor where there's friction, energy is being lost into the universe that I'm not recapturing in my mathematical system. Does that make sense? This is kind of like a very esoteric question. So this is plus work done by non-conservative forces. And for the purposes of life right now, this is always going to be like friction, drag, what do you call it whenever you fall into the water and the water doesn't let you go by, that thing. Okay, so like, yes, either energy can either be created or destroyed, but if I'm only looking at box being pushed across the ground, well, there's this friction, and I guess you can think about, oh, the friction, heat, and that's escaping outside my box of paying attention to. So that's where this asterisk comes from. So if I wanted to redo my analysis where I include the entire universe to push a box across the ground, then great, I could talk about the fact that we've added, you know, some kind of something to the something of the universe. But that's just way beyond the scope of what we want to do. So we kind of adjust this, is that within the scope of the picture that we're looking at, what we're going to say is that the initial potential energy and the kinetic energy plus any work done by non-conservative forces such as friction or drag, that's going to equal. So I remember even the first time somebody said, well, there's this extra thing. And I was like, well, does that mean energy is created or destroyed? No, it just means that it goes outside the box that we're looking at. And this is a big thing in physics, is it's all about what is the box of things that you're looking at. So if you're just looking at box on table, you get one thing. If you're looking at box on table on Earth, that's supposed to be the Earth, then you get another picture. And in that case, maybe if you included all of the weather forces and stuff going on Earth, then you wouldn't need to, subtract out the work done by friction. Because remember, the work done by friction is always negative. So it's like plus the work done by conservative forces, but it's always negative. So you have less final energy than you started with because you lose energy. So even though it says plus work, it's actually a minus sign, and that's just because plus the work done is negative. So that's just the way it goes. So again, if I included box on table in the entire universe, yes, I probably wouldn't need to subtract out the friction work, but I'm not solving that problem because that seems a lot harder than just there's a box across the table and I'm just going to remember that I have to subtract that one term out. Okay, so this is where we go. So I just said MGH, and I'll come back to that in a second, but basically for different kinds of scenarios, but depending on position, there's not a whole lot we're going to get into, probably just gravity and springs is my guess. And kinetic energy is always 1/2 mv squared. For the purposes of this class, eventually if you have something that's like rotating, then it's 1/2 IC omega squared. And so like you have kinetic energy of something rotating, even if it's not actually moving, but I'm not going to talk about that now. I'm just letting you know it does get harder, shockingly. But for the purposes of today, potential energy, and really for the purposes of this whole book, potential energy, kinetic energy, super straightforward. Okay, so this is the potential energy difference. This is just basically getting to what I was saying. So what is the difference in potential energy? That's just going to be the kinetic, basically, plus the work done. So basically what they did at the beginning of time, I guess, is, so if I let me go, initial, I'll show you where they're coming at so you can read this. Initial, let me just make it as 1s and 2s. So potential energy, initial, plus kinetic energy, initial, plus all the other work done by non-conservative forces equals, that's supposed to be an E, it doesn't look like an E. So that equals the final potential energy plus the final kinetic energy. And so if they're asking for a question like, what is the difference in potential energy? So if I go PE2 minus PE1, so PE2 minus PE1 is KE1 minus KE2, right? I can do that. And then plus the work by non-conservative forces. So actually the difference in kinetic energy, because I think this is what we did in chapter 7, right? Because we talked about kinetic energy. Yeah, okay. So the difference in kinetic energy is the work done by conservative forces. Okay, so that's what you end up with. So the total work done is the delta in potential energy, is total work done. Okay, so if my potential energy, it's basically like how much work does it take to get from one position to the next, right? Does that make sense? So this isn't trying to help you memorize it, it's trying to help you understand it. So potential, we said, is based on position. So if I go from a position here to a position here, gravity did negative work, negative, I'm trying to write negative and a negative sign. Gravity did negative work to make that happen. So, and there's actually a negative sign here, so it's the opposite of the total work done. So gravity did negative work. So now I have all of that negative work here. So now I have all that positive work like stored up. So gravity, so it would be, the distance is height, right? So gravity, that's the force times the height if I go up h. So that was the work done. So he did negative mgh work to get me there. Does that make sense? I feel like I'm finally getting to where I wanted to say. So he's doing negative mgh work to get me there. Now that I'm there, I have mgh worth of energy stored up, and that's my potential energy to get me, and I can use that to get back down again. Does that help? If nothing else helps, maybe that helps. So there's like a whole bunch of different ways to think about it, and none of them are perfect because, you know, we're not there yet. The really perfect way to understand it is just to use math and never look at what's actually happening in the system, which is also a terrible way to solve problems in the real world. But maybe that also makes sense. Is the change in potential energy is also your negative the total. Does it actually say negative over here? It does. Yeah, there's a negative. Okay, great. Is a negative the total work done, because it does the work to get you there, and then once you have the work to get you there, what would it take to get you back to your original position? So the work can also, that potential energy could almost be like, what work would be required to get you back to neutral? Okay, and I think that's like really where the chunk is on this. So, for example, if I had a spring here, and this is, I think we were always making neutral. Come here, chicken. Come here, girl. There we go. So if we had, you know, some kind of neutral right here, and the spring was out here, okay, and a distance x away, then what we could say is that the potential energy of spring B, what work would it take to get it back to neutral? It's going to take 1/2 kx squared to get back to neutral. Does that make sense? So the potential energy of a spring is always positive. So the potential energy of a spring is because it's always trying to get back to neutral. The work to get back to neutral is always going in the same direction as the force. So that's another way maybe to think about it. So if I'm sitting here on a, you know, and I have a box, mg, how much work is it going to take to get it back to, say, the neutral position of the ground? Well, it's going to take work of mgh to get back to the ground. So I would say the potential energy of the box is mgh. Does that maybe make some sense conceptually of what's going on here? So that's really what potential energy is. And that's why we also have to say, well, if you go through friction, you also have to add in the friction that would, you know, air resistance and stuff like that you would go through. I'm trying to think. So I guess in theory, and this, I don't think we're going to do this in this class, if for some reason you defined neutral as above you, then you'd have to do, gravity would have to do positive work, and so theoretically this could have negative potential energy, but I'm not going to do that to you today. I think that's probably for a future class. So for the purposes of this, our potential energies are always going to be beautiful and positive as long as you always kind of define the ground as the ground and not the ceiling. Okay, but you can define the ground as the ceiling and then things flip, and that's fine, but then you got to deal with more stuff later. So, wow, that was a whole lot of talking for, it seems like, not that useful. But yeah, I think that's basically what we're talking about here. It's going to be awesome.